Hello, my name is Teodor Tchalakov, a 2024 RIS scholar, and I'll be presenting my work on the Slack Convex Feasible Set trajectory optimizer in collaboration with Simin Liu, Chunglu Liu, John M. Dolan. We are interested in designing a new real-time kinodynamic planner based off the Slack Convex Feasible Set algorithm, also known as SCFS. SCFS is great because it allows us to incorporate the equations of motions that come from dynamic equations explicitly, and it also has fast solve times due to solving convex subproblems iteratively. By using an optimization approach to optimize trajectories as opposed to sampling or graph-based, we can produce high-quality feasible trajectories that are either time optimal or the shortest path. One example of current optimization-based planners are CHOMP, which designs trajectory costs that are invariant to the time parameterization of the trajectory. CHOMP also introduced the usage of pre-computed sign distance fields for collision checking. However, in terms of handling constraints, because it is an unconstrained optimization algorithm originally, only a projection method has been proposed to improve upon CHOMP, but it has not been tested with dynamics. And we can see CHOMP running how CHOMP runs here at the bottom and other various trajectory optimizers. We're taking a start and a goal configuration and creating a trajectory between them. We modify our trajectory by following the gradients of the sign distance fields for these circular obstacles to push the trajectory outside of the obstacles and therefore get a feasible trajectory that is also optimal in terms of either time or shortest path. Another popular optimizer is trajop, which uses a sequential quadratic programming based formulation, which with extra penalty adjustments in order to solve motion planning problems. However, on the side of model predictive control problems, we have differential dynamic programming and its constraint extensions, which allow it to solve model predictive control problems iteratively. However, these approaches can be slow because it requires solving a quadratic problem at each time step for each pass. However, it does handle explicitly dynamics, but not always constraints such as obstacle collision. And then there are also typical general purpose nonlinear solvers such as SQP. However, these might not explicitly satisfy our constraints. Now, when designing a motion planner, we want to have some things in mind. In particular, we want to find maybe the shortest path with the least amount of control effort. And maybe we're constrained by the states and control inputs. And also we might want like a time varying goal / reach constraint on either the position or velocity of the robot. Then we also have initial state constraints, obstacle avoidance constraints, and either kinematic or dynamic model constraints. And it would be nice if our optimizer was robust to naive initializations, had fast solve time, and strictly satisfied our constraints. And if it were easy to formulate, that would be great. So here we can see with a naive initialization, we would expect if our algorithm was robust to initialization to still find a problem even with the straight line initialization. Likewise, for handling obstacles, a sign distance field between two convex objects is the smallest distance between them when they're not intersecting, and the largest penetration distance between them when they are intersecting. However, this value is negative for a sign distance field in order to have a smooth gradient. We assess our contributions over the dynamic conveyor picking problem, which has a time varying goal where given a robot manipulator, we want to have it select a time and location to pick up a box over a conveyor belt that is going at a constant velocity while also satisfying the rigid body dynamics of the robot. And then we also want to make sure it doesn't collide with other obstacles or with itself. So we enshroud it in these capsules in order to do collision detection. And so in our case, we have 15 state variables, one theta for each joint, one torque tau for each joint, and then a time step for each configuration. And then we compute the angular velocity, angular accelerations as finite differences. As such, our conveyor picking problem becomes minimizing the time and control effort, as well as making sure that there are no collisions and getting to the final desired location, satisfying dynamics, start configuration, and any state and control input limits. So in this case, we also have a angular velocity limit. Now, SCFS formulates its problem in the following manner, where we have a configuration for the robot that contains the state and a control. This is then concatenated together to make the entire trajectory for some planning horizon H. Then each trajectory can be constrained in the following manners. SCFS does not explicitly support nonlinear equality constraints, but it does support nonlinear inequality constraints, linear equality constraints, and linear inequality constraints. And it supports the nonlinear inequality constraints if they are continuous, piecewise smooth, in that they are differentiable, and if they also have the property of being semi-convex functions. So the convex feasible set algorithm, given these constraints, produces feasible sets that are convex as a result of these constraints by considering the following. Starting with some reference point, x to the k, or x to the r, without having an index, we place this feasible point, and then we can compute, given 3 different cases, whether or not that specific constraint should be convexified into a feasible set. And then we solve our problem over that feasible set and choose the solution of that quadratic subproblem as the new reference point to our next iteration of our algorithm. And then we continue this until the cost of our algorithm stops changing. So if the constraint is already convex, we do nothing. However, if the constraint has an infeasible region that is convex, then we now have the case where we need to choose a convex feasible set outside of our infeasible region. And so we do this by kind of doing like a linear approximation by exploiting the convexity property of our set in order to say that the yellow region is going to be our new convex feasible set based off of this convex infeasible set. However, if we have a infeasible set that is not convex, then what we can do is we can, given that our nonlinear inequality constraint phi has satisfies this semi-convexity property, what we can do is we can construct the following quadratic set, which if we take a look at the 2 different cases, we'll get a better visualization. In one case, we have the linear convex feasible set where if you're inside, it produces a linear set outside of it. However, if you're outside of the infeasible set, you will produce a feasible set where the point is inside. Similar thing with the quadratic convexification, where if you are inside the set, it will place a convex feasible set outside of it. If you're outside, you will always be inside of the convex feasible set. However, SCFS allows us to handle dynamical constraints by relaxing this nonlinear equality constraint in the following manner. We introduce a slack variable y that is larger and less than the original control variable u, and then we adjust our dynamics, which are the form f of x plus h of x u, such that they are upper bounded and lower bounded by the following equations. This allows us to sort of relax our problem and create a space in between them for which we can create convex feasible sets. The result of this is that the CFS algorithm here on the left has to optimize over this manifold M, which is our nonlinear equality constraint. But when we introduce this relaxation, we can instead optimize over this orange region here, which is much easier. And SCFS has guarantees to conversion to a local optimum for this type of optimization. However, SCFS has a couple of limitations. The first one being that it has, in terms of local optimization, there is no way for it to escape local minimum. And its step size, kind of analogous to gradient descent methods, is the same as SCFS's set size. And so this heavily influences the convergence rates. In particular, because the set size is not necessarily a design parameter if you want to guarantee feasibility. And also, SCFS is not robust to infeasible initialization. This is because we consider the fact that an initialization will create a set of quadratic constraints, and that quadratic constraint, all those quadratic constraints which are made must have a non-empty intersection in order for the program to begin running. And as a result, this makes it difficult when you initialize with constraints that can conflict with each other. So in order to assess the robust initialization problem, we note that we can check convexification. We can do convexification and check feasibility quickly, and therefore we can run these procedures multiple times. And so we consider doing a naive uniform trajectory sampling or sampling with some sort of context in order to make the constraints, more of the constraints be satisfied during the initialization as opposed to having it be randomly satisfied. And then we also introduce performing a feasibility search using SQP, where we put our original problem into SQP, and then we set the objective function to 0 in order to find a feasible point based off of some infeasible initialization. So in a sense, we're turning our constrained problem into a unconstrained optimization problem. And in our case, for the dynamic conveyor picking problem, we know where we might want to place the end effector from the start position towards the goal position. And then maybe we want to choose an intermediate waypoint for this strategy. So in particular, this is what that initialization will look like. We have our goal, our start, and our waypoints, and we can interpolate in between them. On the other hand, we, in order to reconstruct the torques, we use inverse dynamics in order to, given a current state, select a torque that satisfies that current state in the dynamics. And then we choose our time steps to be uniform. Now, after running the experiments for this with 10,000 iterations of performing our initialization strategy over our problem, we can see that these uniform sampling strategies that are with or without context have a very low initialization success rate. And this is pretty clear in that our dimension is 150 variables. And so it's very, it becomes exponentially unlikely that we will initialize into a feasible region. But this also suggests that our feasible region is actually quite small. And even though these naive initialization methods are quite fast, they aren't particularly useful in that SCFS doesn't run any initializations because it cannot initialize correctly at the beginning. Now, on the other hand, if we take these naive initialization methods and we perform a feasibility search on them using SQP, we can see that the success rate drastically improves. And in fact, even though the initialization time takes a bit of a penalty, we can see that if we choose a more smart initialization, such as the SWG joint linear interpolation with uniform goal sampling, we see that the initialization time with SQP is actually lower than in the worst case uniform sampling. This is because if we choose a better initialization that has more constraints that are satisfied as opposed to less constraints, then our result is that we can, as a result, SQP will take less iterations in order to solve our problem, which is great because that means we can run SCFS with a higher initialization success rate and we can do it in less time. We can initialize in less time. So as a result, here's our MATLAB implementation and solution of the dynamic conveyor picking problem, where here on the left, we can see our objective function is decreasing and that our solution compared to the initialization is changing. And likewise, the final trajectory shows the robot going from its start position to picking up the object. And then to take a look at how long it takes for these objects to be, for each iteration of SCFS to be computed, we can see that solving the quadratic subproblem doesn't take a lot of time. It takes around 40 to 50 milliseconds on average, while performing the pre-computation cost, the convexification in MATLAB takes 2 seconds on average. And this is mainly an implementation detail, but we believe that this will be quite straightforward to implement quickly. So I would like to thank the advisors, mentors, and sponsors that I have been fortunate enough to work with this summer for making this experience as wonderful as it is. In particular, I would like to thank Simin Liu, Dr. Chunglu Liu, Dr. John M. Dolan, and Rachel Bershin for making sure that this experience would be as fruitful as it is. Thank you.